Picture a thin strip of metal, stretch it, and for a second it actually warms up in your fingers. Let it snap back and it turns properly cold, not room temperature cold, cold enough that you'd notice immediately. That's not a magic trick, that's a real material being tested right now in a lab in Germany as part of a serious attempt to build an air conditioner with no refrigerant gas inside it at all. None. Zero. And it's not the only one. Right now, there are at least 4 completely different ways to cool a room without a single drop of the chemical that's been sitting inside every air conditioner and fridge for the last 100 years. One uses a stretchy metal, one uses a squeezed-down crystal, one uses actual magnets, and one just runs electricity through a solid block and lets the heat walk out the other side. By the end of this video, you'll understand all 4 of them and why the timing here is not a coincidence. Section 1, the trap Europe is walking into. Here's the thing about your air conditioner and pretty much everyone else's. It hasn't fundamentally changed in over 100 years. Willis Carrier built the first modern one in 1902, and the core idea has stayed the same ever since. Take a gas, compress it into a liquid, let it evaporate back into a gas, and use that cycle to drag heat out of a room. Every fridge, every car AC, every office chiller does some version of this. The gas doing the work is called a refrigerant, and for most of the last century it's had a nasty side effect. If it leaks, and it does leak from old units, careless disposal, tiny cracks in a line, it's absurdly good at trapping heat in the atmosphere. One of the most common refrigerants in use today, especially R410A, still standard in many places, has a global warming potential over 2,000 times higher than carbon dioxide, pound for pound. Put another way, the refrigerant sitting inside just 5 ordinary air conditioners, fully leaked, would warm the planet about as much as driving a car for an entire year. Here's the trap: the EU has decided enough is enough, and it's phasing out these high-warming refrigerants. Soon, new air conditioners and heat pumps that use them won't even be legal to sell there. At the exact same time, Europe needs air conditioning more than it ever has. In June 2026, parts of the continent hit over 40 degrees Celsius. And people were scrambling into stores in France to grab a portable AC unit or a fan before shelves emptied out. Right now, only around 1 in 5 European households has air conditioning. In the UK, it's closer to 1 in 25, compared to roughly 9 in 10 homes in the US. That gap is closing fast. The International Energy Agency expects 2/3 of homes on Earth to have AC by 2050. This isn't just about comfort either. Access to air conditioning has been linked to fewer deaths during heat waves. One estimate puts the number of heat-related deaths avoided among people over 65 worldwide in 2019 alone at close to 200,000. So Europe is caught between 2 walls closing in at once, a booming need for cooling and a ban on the one chemical that's cooled almost everything for a century. Which is exactly why, in labs and pilot buildings across the continent right now, people are testing ways to cool a room using no refrigerant gas whatsoever. Section 2, enter solid-state cooling. So how do you cool something without a refrigerant? You use a solid instead of a gas. There's a small family of materials that change temperature when you do something physical to them: stretch them, squeeze them, magnetize them, or run current through them. Scientists call this a caloric effect, and there are 4 flavors of it being tested right now as real, working air conditioners. Let's go through all 4, starting with the one that looks the most like a magic trick. Section 3, Elastocaloric, the metal that breathes. At Saarland University in Germany, a team led by engineer Paul Motzke is working with an Irish company called Exergyn on a system built around a shape memory alloy called nickel titanium, the same family of metal used in some eyeglass frames and medical stents, because it can bend and spring back to its original shape almost indefinitely. Here's the trick: stretch a wire of this alloy and its internal crystal structure flips from one arrangement into another. A phase change, kind of like water turning to ice, except it's happening to a solid metal, and it's triggered by mechanical force instead of temperature. That flip releases a burst of heat. Let the wire relax back to its original shape and the structure flips back, and this time it pulls heat in instead, cooling anything nearby. So the whole air conditioner is really just stretch the metal, dump the heat outside, let it relax, pull heat out of the room. Repeat that thousands of times and you've got a working cooling system with no gas anywhere inside it. Early tests suggest this can drop indoor temperatures by 5 to 10 degrees Celsius, and it may end up more efficient than a standard air conditioner. Motzky has said the technology could represent a genuine paradigm shift, simply because it works on a completely different principle than anything the cooling industry has used before. Exergyn is aiming to get it into new buildings within the next few years, not a lab demo, an actual product. But stretching metal is just option one. Some researchers went even weirder with something that behaves like a magic rock. Section 4, Barocaloric, the crystal that acts like a stress ball. A company called Barocal, spun out of the University of Cambridge, builds heat pumps around something called a plastic crystal, not plastic in the milk jug sense, but a solid where the molecules are still free to spin and tumble around, almost like the material can't decide if it wants to be a solid or a liquid. Founder Xavier Moya likes to explain it with a rubber balloon. Stretch one out and it actually warms up slightly in your hands, let it snap back and it feels cool again. His plastic crystals do something similar, but far more dramatically under pressure instead of stretching. Squeeze one and the tumbling molecules suddenly lock into a more ordered arrangement, and that drop in molecular disorder releases a real, usable amount of heat. Release the pressure, the molecules go back to tumbling, and that reabsorbs heat from whatever's around it, cooling it down. It's a strange thing to build a fridge out of, a soft, waxy solid you could squeeze in one hand. But Barocal has already raised $10 million to bring it to market, backed by climate-focused investors, and the underlying material has been shown to perform surprisingly close to the refrigerants it's trying to replace. 2 down, but if squeezing a solid feels almost too normal, wait until you hear about the version that uses magnets. Section 5, Magnetocaloric, cooling with magnets. Then there's the option that sounds the most like science fiction, cooling with magnets. A German company called Magnotherm, spun out of TU Darmstadt, builds systems around metals that heat up when exposed to a strong magnetic field and cool back down the instant that field switches off. Push water past the metal at the right point in that cycle, and the water carries the cold away into a fridge, a display case, eventually a whole room. This one already has a track record. Magnotherm's first product was a magnetically cooled drinks fridge that Coca-Cola put into actual use. Its newer unit has been piloted inside a major German supermarket chain, and in that trial it used about 15% less energy than the propane-based system it replaced, while holding food at exactly the same temperature. The plan is to prove itself in supermarkets first, then scale the same trick up into full building air conditioning. 3 down, 1 to go, and this last one doesn't stretch, squeeze, or spin anything at all. It just pushes electrons through metal. Section 6, Thermoelectric, heat that flows like electricity. A company called Mimic Systems is building what's called a thermoelectric heat pump. Run an electric current through a block of semiconductor material, and it drags heat from one side of the block straight through to the other. No phase change, no fluid, nothing physically moving, just heat riding along with a flow of electrons. It's the same underlying effect already used in some small portable coolers, just built at a much bigger scale. Mimic's version is modular, small blocks stacked together like building a wall out of Lego to scale up from a single room to an entire apartment building. With 0 moving parts, there's nothing to wear out and nothing to make noise. Their first real pilot is already running, installed in an apartment in Vancouver for someone whose medical condition makes it genuinely dangerous to be stuck without reliable cooling in the heat. A good reminder that this isn't only about the planet. For some people, quiet, dependable cooling is a matter of basic safety. The recap. So that's all 4. A metal that goes cold when you let it spring back. A crystal that goes cold when you stop squeezing it. A magnet that goes cold the instant you switch it off. And a semiconductor that just pushes heat through itself like a wire pushes electricity. 4 completely different branches of physics, and every single one ends the exact same way. A cold room and not one molecule of refrigerant gas. Section 7, the reality check. Before this sounds like a solved problem, it isn't, not yet. Lindsay Rasmussen, who works closely with climate tech startups, has been blunt about it. There's real promise here, but none of it is proven at a large, real-world scale yet, and how fast that changes depends on whether serious capital and manufacturing partners get behind it. All 4 companies we just covered are still working with small pilots: 1 apartment, 1 supermarket chain, a handful of buildings. None of them are anywhere near replacing the billions of conventional air conditioners already installed worldwide. Whether any of this reaches your house may come down to something almost boring: whether a handful of giant manufacturers decide to adopt and mass produce it, the same way they did with vapor compression a century ago. And even if every one of these succeeds, hardware alone won't fix Europe's heat problem. A lot of European buildings were built to trap heat in, not keep it out, and dense cities make that worse. Planners keep pushing something called a cooling hierarchy: block the heat first with shading, airflow, and reflective surfaces, and only then bring in a machine. Paris has already leaned into this, expanding a district cooling network that pipes chilled river water underground to cool public buildings. No individual AC units required at all. Section 8: Old Physics, New Math. Here's what I find genuinely interesting about all 4 of these. None of the physics is new. The effect powering that stretchy metal wire has been studied for decades. The magnet trick is over a century old. Running current through a semiconductor to move heat has been known since the 1800s. None of this needed a brand new discovery. It needed the climate math to finally get bad enough and the regulations to finally get strict enough for anyone to take old physics seriously as a way to cool an actual building. Vapor compression has had basically zero real competition for over 150 years. If even one of these 4 ideas scales the way LED bulbs quietly replaced incandescent ones, this could be one of those shifts that doesn't make headlines on the day it happens, but completely reshapes an entire industry within a couple of decades. If you want a full deep dive into any one of these 4 effects, the metal, the crystal, the magnet, or the semiconductor, tell me which one in the comments and I'll build the next video around it. And if the physics was hiding in plain sight the whole time is the kind of story you're into, that's basically this entire channel, so go ahead and subscribe. Because the next time cold air hits your face, it might not be gas moving anymore. It might just be a piece of metal remembering how to be cold.